Good afternoon and welcome to Advanced NMR Spectroscopy course. So I have completed the chemical sheet. So today I will start spin coupling. So if you have any doubt on chemical sheet, you can send an email or you can ask me after the class, this class is over. So now I'll first start with first order spin coupling. Now first order is also known as weak spin coupling. That means the two coupling nuclei, the nuclei which are coupling to each other, they have a quite wide chemical shift difference. Okay, so when they have a large chemical shift difference, we call them weak coupling. Okay, and under weak coupling we see the spectra, those spectra are called first order spectra. Okay, so we will see when the chemical shifts are very close. Okay, then we'll see different thing, but we'll come to that in the last class. Okay, we'll start with the first order weak spin coupling. Okay, now you see I have shown you the two spectra here. One is methyl acetate, another is ethyl acetate. The left hand side is methyl acetate. You can see there are only two single lines. One is at 2.050 delta, another is 3.662, and their integration also 1:1 or 3:3. But if you see in the right hand side is the ethyl acetate. It has got three sets of peaks. One, you can see there are three lines at 1.260, that is accounting for 3 protons, one methyl group, and then you will see a single line that is also accounting for 3 protons, and another 4 lines that is account for 2 protons. Okay, that is so you can easily assign them as according to their chemical shifts, because as we know the chemical shifts, so we can assign them which methyl is which methyl. Okay, and of course the CH2. Okay, now if you see this in case of ethyl acetate, the spectrum appears very complex. Okay, because of this additional lines you see in the spectrum. Okay, but although it is building complexity, but actually it is very useful. Sometimes it is complement to the chemical shift data to tell which proton, which group of protons is which one. Okay, we'll see. For example, here you can see the CH2, there are 4 lines, CH3, there are 3 lines. So there are some relation between them. See, CH3 is becoming 3 lines and CH2 is becoming 4 lines. Okay, we'll see all those things. Now I will take another example, the spectra of diethyl ether. Okay, so you know that the molecule is having a C2 axis. Okay, that is shown there. The C2 axis is being shown here, and also the sigma plane. And so automatically you see these two CH2s and these two CH2s, they are chemically equivalent. That means they come in the same place, they have the same chemical shift, and their chemical shift is at 3.48 because they are attached to oxygen. And then these methyl group and this methyl group, they are also chemically equivalent, and their chemical shift is 1.21. Okay, so now if you see that okay, so there are, if you see that there are 3 line, I will call this as a triplet. Okay, I will go to later on this nomenclature. So 3 line timing, consider this is a triplet. So there are 6 equivalent hydrogens which are coming from the 2 methyl groups. These 2 methyl groups are coming there. The chemical shift value is also 1.21 ppm. Similarly, this at the 4 lines which are coming at 3.48, actually it is equivalent to 4 equivalent hydrogens, that is due to the 2 CH2 groups. Okay, and if you see the difference between this line here and as well as here are 6.9 hertz. We'll come to this a little bit late. Let us see. So the signal which you see at 1.21 ppm, it is a 3-line pattern with intensity. If you see, their intensity is 1:2:2. This is 1, this is 2, this is 1. So 1:2:1. So if the line intensity line ratio of these lines, it is this ratio is 1:2:1, then we call this is a triplet. Okay. And if you see the central line, is the chemical shift value, that is 1.21 is the central line falls on the delta value 1.21. So this is the chemical shift position of the methyl group. Now the spacing between these two lines, any two lines, is 6.9 hertz, is known as the coupling constant. We'll come to discuss detail later on. Okay, so just I make you remember this is the coupling constant and the chemical shift. So chemical shift is nothing but the position of the central line. Okay, and the difference between these two lines, okay, is the coupling constant. Same thing for this 3.48 is a 4-line pattern with intensity ratio. If you see, is equal to 1. This is 1. This is 3. This is 3. This is 1. Okay, so this is called a quartet. Okay. And if you see in case of quartet, the chemical shape will be the average of this line. You have to take the average position of these two lines. Okay, in this case actually it is the middle line, but in this case you have to take the average of these two lines in chemical shift, and that will be your chemical shift value, and that is nothing but 3.48 ppm. Okay, and again you see here also it was 6.9 hertz, here also 6.9 hertz. Okay, so that's the coupling constant. If you see that the triplet and quartet, the coupling constants are same. Okay, and also the integration, if you see, this corresponds to 4 protons and this corresponds to 6 protons. Okay, so the relative peak area also gives you as it is expected. So due to the splitting of the signals, there is no change in the area of the peaks. So now see, I have told you about the when you have a 3 lines or 4 lines. Okay, now so in many times you will see that there are more number of lines. So how to represent them? So representation of a multiplicity of a signal is shown here. Suppose if you are getting only one line in a spectrum, this is called a singlet. Like if you see ethyl acetate, one methyl is coming as a singlet. So 2 line you will see called a doublet. So 3 line triplet, then 4 line you are getting quartet, 5 line we call quintet, 6 line is sextet, 7 line is heptet, 8 line is octet, 9 is nonet. And if there are, you will sometimes see in some spectra you are getting many lines, then you call them a multiplet. Okay, and normally when you tell this singlet, doublet, triplet, so in that case you give the center value of the multiplet as the chemical shift. But when you get a multiplet, you have to give the delta range. That means where from the multiplet start, like let us say you are getting like a multiplet like this. Okay, so your chemical shift range value will be starting from here to here. So let us say this is 1.3 and this is 2.4. So delta value will be 1.3 to 2.4. This is. Whereas if you get, let us say, singlet like this, okay, and this chemical shift value is let us say 2.05, then you will report it as a 2.05. Okay, in case of doublet, you will take the average of these two lines, so that will be your delta value. Triplet, as I told you, so this middle line will be your delta value. Quartet will be the like doublet. You have to take the average of middle two lines. Okay. Now you will see the when we talk about the couplings. So you will see that we will be using sometimes this one symbol that is called the J. Okay. So one symbol is that we will be using this singlet, doublet. Sometimes you can write that in S, D, T. Okay. And then you will have the another term is your J value. Okay. Now J can be so now in this particular case you see that when the hydrogens are attached to the same carbon, okay, so you can see there are two bonds. So these two hydrogens are at two bond distance. This is the bond 1, this is the bond 2. So they are at two bond distance. So we call them as a geminal. It is a standard coming from organic chemistry. When two hydrogens are attached to the same carbon, we call the geminal carbon, geminal hydrogen. Okay, so these are two are geminal hydrogens, and how many bonds are there? Two bonds are there. So that's why these two represents J tells the coupling constant. We'll be writing the value. So it will be 2J. Okay, so 2 is coming from how many bonds are there between the interacting nuclei. See, so in this case also these are also called 2J and it is also geminal. So this is called vicinal. They are the adjacent carbons. Okay, you can see these two hydrogens are 3 bonds away. So that's why they are called the 3J. Now when you take a alkene, you can have now again they are vicinal only, 3 bond A, but there could be two stereochemistry. One is the cis, that these two hydrogens are at the same side of the double bond. In other case, these two hydrogens are in the opposite side. So they are vicinal, 3 carbon, and we call them 3J trans. Normally, the couplings you will see in most of the cases, the coupling beyond 3 bonds are very difficult to visualize. But certain specific cases we can see, like allylic system. Okay, that these two hydrogens are 4 bonds apart. Okay, so you can see we call them 4J. Similarly, in aromatic system also you will see that you can see a 4 bond coupling, and this is called homoallylic. So this is a 1,5. There are 5 bonds in between. So this is a 5 bond we call 5J. So this number left hand side superscript is nothing. It tells about how many bonds are there between the interacting nuclei. Okay. Now let us see what will happen if you change the spectrometer frequency. Let us say you are recording a NMR in a 250 megahertz machine, and you see the delta nu. If you remember those two chemical shift of the methyl, methyl group is 1.21 for diethyl ether, and 3.48 is the CH2 group. And if you so delta nu is 3.48 minus 1.21 ppm into nu 0 is 250. Let us say you are measuring the recording the NMR 250 megahertz. So what is the difference between these two group of protons in terms of hertz is 568 hertz. If you record in 400 megahertz, you see that now changes. So if ppm value does not change, like if you remember what is the definition of delta. Okay, but if you change the machine frequency in terms of frequency, it is changing. Okay, now recording 100 megahertz, you see it is 227 hertz. Okay, so if you, what we see is that the chemical shift difference in hertz units changes with spectrometer frequency, but the delta value does not change, that we know. But the coupling constant do not change. If you remember that this is the most important thing you have to remember, the chemical shift difference in hertz unit changes with spectrometer frequency, but the coupling constant do not change, and it remain 6.9 hertz in all 3 spectrometer frequency. So what is the gain from that? So in case of 400 megahertz, you see a better spectral dispersion, while in 100 megahertz, relatively poor dispersion in spectral lines. Okay, so I will explain you this with one example, spectral line. What do you mean by spectral dispersion? I will take a very simple example. Okay, you know the valine. Valine is a amino acid. Okay? Okay, so you have now in case of Valin, if you see, draw the stadium. So this is a chiral center. Okay, so as if you remember, the groups, equivalent groups attached to near to a chiral centers are not chemically equivalent. So this CH3 and this CH3, they are not chemically equivalent. Okay, so that means they have different chemical shifts. Okay, so now let us see. So if you see, if you record their NMR, let us say you record NMR. Let us say they come around 0.95. Let us say in one case, and or will for simplicity 0.90 and 1.1. These are the delta values of those. Okay, so now let us write this. Let us make it is 1.0. This will make it 0.9. We'll make it 0.8, 0.7, 0.6. We'll put similarly this side 1.1, 1.2, 1.3 and 1.4. Okay, so this let us say this is coming as a J is equal to 6 Hertz. Okay, for both, let us assume J is equal to 6 Hertz. Okay, this is for your understanding. Okay, so and assume that this methyl is coupled to this hydrogen, so we'll get a doublet. Time being, we are not considering the coupling with this methyl. Okay, just this is coupled to this hydrogen, so you will get a, so let us say this is a 60 megahertz spectra. So 60 megahertz means 60 hertz is equal to 1 delta. Okay, so 0.1 delta is 6 hertz. Okay, so what you will see, a, this is, sorry, so 6 is, so you have, so you will see that this is this, if you consider that this, the middle point will be, if you see that this distance will be 3 hertz. Okay, so you will get a, similarly this. Okay, so this is 6 hertz. And this is the chemical shift. I told you 0.98. Now the second one is also, let us say, so you get at this position. So, and that will fall on this. Okay, clear? Because this is also 6 hertz. So this side 3 hertz and this side 3 hertz. Okay, so now how to know whether it is a triplet? So the initially this intensity was, this will be 1, this will be 1, and then there was 1 and this was 1. So now it has become, the overall intensity has become 1:2:1. Okay, so this is a situation in 60 megahertz. Okay, now you change it to, so what will be its position? It will be 0.85 delta. This will be coming at 0.95 delta, and this will be coming 1.05 if you see in delta value. Okay, now you change it to the machine to a, let us say again, I'll put this as a 1.0, 0.9, 0.8, 0.7, 1.1, 1.2, 1.3, and now let us see, we have moved to now to 300 megahertz. Okay, so 1 delta is equal to 300 hertz. Okay, so now again you will get a doublet here with the same. Okay, same you will get now, you get a doublet here. Okay, and this difference is again 6 hertz. This difference is also 6 hertz. Okay, now you see the values. So this will be, what will be the value of this? Okay, so it will be 0.8. You can find out. So 3 hertz is 0.89. This will be sorry, yeah. Thank you. So 0.89, and this will be your 0.91. This will be 0.99 and 1.01. See, you now see that if you see in earlier case, see the chemical shift values, if you consider the delta values, you see that's why there is overlap. Now as the J value does not change with the machine frequency, so now clearly the two doublets got separated out. So this is the advantage. So this is called the spectral dispersion. When you record a spectra in a low frequency machine, you may get a spectral overlap, or there could be peaks overlap. But you see now, as the J remains constant, J is constant, okay, in terms of hertz, and delta changes in terms of hertz. Okay, so that's why you get the spectral dispersion. Now let us see why this splitting occurs. Okay, so what do you mean by there are two lines? That means there are the molecule is absorbing the radio frequency at two different frequencies. Okay, or the nuclei is having two different precessional frequency. Okay, that's why you get now when you have a different chemical shift, you get two, that is happening due to the two different precessional frequencies. So when a line splits into two or more lines with different precessional frequencies, what does it mean? It means a fraction of the collection of the same nuclei is experiencing different field. Not all the molecules are experiencing the different field. A fraction of the collection of the same nuclei. That's why instead of one line, you are getting two lines. Sometimes you are getting 1:1. Sometimes you are getting 1:3:1:2:1. Sometimes you are getting 1:3:3:1. So that means it means that a fraction of the same nuclei is experiencing different field, thus different precessional frequencies. Okay. So why it is happening so? Okay, and first thing is that why it is happening, and then how this fraction of the collection of the same nuclei are decided. Okay, we are telling now 1:1, 1:2:1, 1:3:3:1, like that. How it is decided. Now let us consider the diethyl ether, the CH2 group of diethyl ether, and each of these hydrogens. Now if you consider each of these hydrogens, okay, they can be in the alpha state or in the beta state. So each hydrogen having two spin state, alpha and beta, and they are equally populated, because if you consider the magnetic field, their population difference is very small. Okay, if you remember, although we are getting NMR spectra due to their small difference, but you can tell them nearly equal. Okay, they are in million ppm. Okay, so we can say that these two are equally populated. Okay, and we know that they have the same precessional frequency, hence same chemical sheet. Okay. So what we have seen that the CH2 group of diethyl ether, there are two hydrogens and each one can be in alpha and beta state with equal probability. Okay. So if you consider that now the two hydrogens together, they have the four possible combination of spin state. Okay. If you consider two hydrogens, so they can be both can be alpha, then that state we call alpha. They can be both beta, we call beta state, or they can be beta alpha. One spin is alpha beta, another is alpha. In second combination, the first one is alpha and second one is beta. And if you see these beta alpha and alpha beta states have the same energy, because they have the same precessional frequency. Okay. Now, if you consider that, what will be the resulting spin state? If you add these individual spins, what will be the resultant spin state, which I have shown here. Okay. So you can see that when you both the spins are in the alpha state, these and these. Okay. So the M value for that state is 1. Now this I have told you the beta alpha and this is beta alpha and alpha beta, they have the same energy. So this is your applied field and this is your energy, and you can see the M value is 0 for that. Okay, if you add their M values, and here it is -1. So you can see now the CH3 group, okay, each of these CH3 group is seeing a combination of this type of situation, because the CH2 group can have now 3 different arrangements, both alpha, one beta, and both beta. But 1 alpha, 1 beta, there are 2 possible combinations. So there are 2 weightage is 2. Okay. Now what this tells, because they do not have the same M value, so you can consider them like that. They are like minute fields. Okay, due to this magnetic moments. Okay, they are different small quantity of magnetic fields which are inherent from the individual nuclei and are independent of the external magnetic field. That's why you can see the J values are always constant. Why? Because they are inherent from the individual nuclei. They have nothing to do with this alpha and beta has nothing to do with the applied magnetic field. Their magnetic moments are independent of the magnetic field. That's why the J value remains constant. Again, we'll come to that. Okay, so these small moments cause minute changes of B effective experiencing by the neighboring nuclei. That means whatever small due to this arrangement, each group are making a different kind of magnetic field around the methyl protons. Okay, so here are 4 possible such small different B effective. Okay, and as these moments are field independent, they remain constant and called coupling constant, that I told you. So the CH3 signal in diethyl ether split into 3 lines with intensity, you can see from here, 1:2:1. Okay, because of this type of combination. So this part is, I hope this part is clear. Now let us see about so I have shown here. So you can see the CH3 feels 1/4 fraction of CH2 in M-1 state. Okay, it is 1/4. Na? There are 4 possible arrangements. So it is 2/4 with M is equal to 0, and 1/4 is equal to M is equal to +1. So when there is no effect, that actually gives you the delta value or chemical shift value, because there is no effect of B effective is the same as the what you are getting during the chemical shift. Okay, there is no further change. Whereas in M1 there is the field is added, M-1 the field is subtracted. Okay, small amount that is coming from the nucleus and that is independent of magnetic field. Okay. Now let us see the CH2 group. Okay, how it is affecting the CH2. Now this part is very clear. Okay, so if there are, I have given a general statement here, if there are n number of equivalent nuclei, if there are n number of equivalent nuclei spin value y, they can exist 2i plus 1 to the power n state. Now when for methyl group there are this will be 2I is nothing but I is proton is half, so this will be T, so it will be 2 to the power 3. So there will be total. So for 3 hydrogens, possible spin combinations are 8. And out of that 8, there will be 4 different spin states. Okay, so spin combinations are 8. Okay, whereas different spin statements, they will have different m values, summation of m values, or different energies. Now you can see from one spin state is all the nuclei, all the 3 hydrogens are in the alpha state. In the second group or second combination, you can see 2 are alpha, 1 is beta. So there are 3 possible such arrangements. The second is that 2 are beta, 1 is alpha. There are also 3 possible arrangements. And the third possible arrangement is the all 3 are beta. Okay, now if you see their probabilities. So if you see this CH2, the fields 1/8 fraction of CH3, because it is the total 8, only one group is there. Okay, so it is filling 1/8 fraction of CH3, that is in the M3/2 state. Similarly, here it will be 3/8 fraction. These also 3/8 fraction, and these also 1/8 fraction. So that gives you the relative intensity of the peaks. Okay, and this, the difference between these is again nothing but the coupling constant. Okay, so CH2, that's why CH2 is appearing 4 lines with relative intensity of 1:3:3:1 with equal spacing between the lines, which also matches between the C. If you see what about the difference you see here, that was also there in case of CH3 group. Okay, and you see now the delta value is not this, you have to take the average of these two. Okay, that will give you the delta value. Okay, so the average value, average position of line 2 and 3, if you put the line number 1, 2, 3 and 4, the average position of the line 2 and 3 will give you the chemical shift. So this happens always. If you have a odd multiplicity system, then you will see that your central line will be the chemical shift. If it is even, you have to take the average of the middle two lines. Okay, so a very important statement is that if a nucleus A coupled to B, okay, so a nucleus A coupled to nucleus B, A coupled to nucleus B, then nucleus B will also couple to nucleus A. Okay, ऐसा नहीं है that only A will couple to B or B will couple to A. Okay, and the coupling constant J will have the same magnitude, JAB equal to JBA. Okay, this is the most important thing you should remember. Now, what are the requirement required for spin-spin coupling to take place? So, for two nuclei to engage in spin-spin coupling, both must have spin 0. Okay, it cannot happen then to carbon 12 is coupling with hydrogen. Okay, it has to be, if it has to, it has 30. So both must have spin I equal to 0. The coupling nuclei must be non-equivalent. Okay, this is the timing you remember that non-equivalent nuclei only couple, but you must remember the coupling of equivalent nuclei is also possible. Okay, it actually happens, but it is not visible. Okay, I'll tell you why. That will be my third lecture on spin-spin coupling. Okay, so equivalent nuclei also couple. Okay, they must preferably be separated by 3 or fewer bonds. Okay, see this coupling happens, they are not coupled in space, so this coupling happens through the bonding electrons, through the bonds. Okay, so if you go away, because the nuclei will couple with electron, then electron will couple with another electron, then it will go to the next nucleus. Okay, so beyond 3 bonds, this is becomes, the value becomes so less, it is not visible, or it matches with the natural line width. Okay, a natural NMR line width, and you must know what is natural line width. It decided by the lifetime, and I have told you the NMR spins lifetimes are around seconds. Okay, okay, or just it is around 0.5 to 0.5 or more seconds. Okay. But you will see that beyond 3 bonds also we will see in exceptional cases. I have already told you allylic coupling and homoallylic coupling. Now to find out, so there is one rule called N+1 rule, and it is mostly used in proton NMR spectrum. Okay. So what we have seen that we have two equivalent nuclei coupled to neighboring hydrogen gives a triplet. When there are 3 equivalent nuclei, they are giving quadret. Okay. So if a nucleus has n equivalent nuclei neighboring hydrogens, okay, n equivalent neighboring hydrogen, you will see you will get a N+1 lines. So that's from that only this N+1 rule is coming. This is because the n neighboring hydrogens, okay, can generate N+1 different spin state. If you remember, I have explained you when there are 3 protons, we have generated 4 different possible M values. Okay, one with all 3 alpha, one with all 3 beta, and there will be 2 more different type of combinations. Okay, so you can generate N+1 different spin state from combination of 2y+1n, that is nothing but 2 to the power n number of possible spin states. Okay. If another, now I'll show you one example later on. So if another, suppose there are in a molecule one CH2 is, let us say one group of proton is coupled to 2 different groups of protons. Okay, which are not chemically equivalent. So what you have to do that in another which different from the first group, the effect of the second group must be considered separately. So you consider first the coupling with one group and then you consider the coupling with the second group. Okay. For example, I have shown you here, if 2 groups of protons like HA and HB are coupled to a group of proton HC. Okay, so coupling of HC with HA and HB, where H and HB are of different groups, they have different chemical shift. Then the effect of coupling on HC is same irrespective of considering HA coupling first or HB coupling first. You have to take them as separately coupling, but you can first show the coupling with HA and then HB, or you show first HA and then HB. I will show you with one example. Okay, the example is right here. Now you see this molecule, you have 3 different hydrogens, HA, HB and HC. Okay, and I have also given some conditions. The JHBHC, this means the coupling between these two, J is larger than the coupling between okay. So this is JBC greater than JAB. That only I have written here. Okay. Now let us see how the HA will come. Now HAC, you have to see only these hydrogens within 3 bond distance, and there is only one hydrogen, so it will become a clean 1:1. The ratio will be 1:1 doublet. Okay, and the chemical shift value will be this will be your chemical shift value. Okay, and the difference between these 2 lines is called the coupling constant. Now come to HB. HB is 3 bond away from HA and 3 bond away from HC. So there are 2 couplings. If the 2 couplings are same, we will discuss later on. Let us say assume the couplings are different. Okay, so and I have told you the JBC. So you can show the JBC first, that coupling is constantly larger. So you have shown that, and then each line will be split by HA. That also I have shown. So you are getting a 4-line spectrum, a doublet of doublet with all intensities are same. Okay, all same. Okay, and then the last proton is HC. HC is only coupled to HB because it is only 3 bond. The other one is 5 bond away. Okay, so you are getting JHB. So that is same. Now you see this JHBAC, HBHC, and this JHBHC are same. Okay, so you get this pattern. Now let us say, as I told, I have considered first the larger coupling constant and then the smaller. Let us say I'll consider the first smaller coupling constant. Okay, then also you get initially a 2 lines doublet, and now this each line you are making with a larger coupling constant. So this is your larger coupling constant. Okay. Again, you see the appearance is same. The intensities are also same. So whether you are considering the first group first or second group first, it does not matter. The appearance of spectrum will remain same. Now let us see if the coupling constant of this HA and HC to HB is same, then you have to the number of lines will be N1 plus N2 plus 1. In that case, you will not get a doublet of doublet, you will get a triplet. So what will happen? These two will merge. You see, if these two are same, they will merge here and you will get a triplet. Okay. So even when the coupling constants of two groups are very close, okay, less than 1 hertz, you may see you may see number of lines will be again N1 plus N2 plus 1 until unless the machine resolution is very high. Okay. And the line separation corresponds to the coupling constant that I have already told you. I have shown you one, okay, relative. Now let us see what will be the relative intensities within a multiplate. So there is a mathematical way to represent what should be the relative ratio of the each peak in a multiplate. So they follow the coefficients of binomial distribution, which I have shown here. The mathematical 1 is to n by 1 is to n into n minus 1 by 2 into 1, like that. So it is a coefficients of the binomial distribution, and you can also very easily follow it from called the Pascal triangle. Pascal triangle, if you see that when you do not have any neighboring nuclei to interact, then your spectrum will be a singlet, and then the intensity ratio will be 1. But if you have one neighboring nuclei interacting, so you will get a 2 doublet, and the intensity of the lines will be 1:1. Similarly, triplet, I have up to triplet and quartet I have explained to you. So if there are 4 equivalent nuclei, you will get 5 lines, and the relative ratios you can see 1:4:6:4:1. So that will give you a quintet, and if there are 5 protons equivalent, will get a sextet. Okay. The most important thing is that this coupling constant values, they can be positive or negative. So far I have not told anything about their sign. I have already told that yes, they can be positive or negative. But irrespective of whether they are positive or negative, the splitting pattern is independent of the sign of the coupling constant. And the appearance of the spectrum solely depend on the magnitude of J. This is true only for first order spectra. Okay. When you go for second order spectra, I will see this is not true. It depends on the relative sign of the coupling constant. We'll see later on. But time being, for all simple spectrum, you remember that whether J is positive or negative, it does not matter. It depends solely on the magnitude. Okay, the magnitude of spin-spin coupling constant, as I was telling you, that it decreases as the number of intervening bonds between the coupled nuclei increases. As I told you, now we'll see later in the next class that how the bonding electrons are involved in this process. Okay, so this is a typical spectrum I have shown for isobutyl alcohol. If you see, there are 4 different groups of proton. The methyl comes around 0.91 ppm, the CH comes at 1.76 ppm, and then the hydroxyl proton comes at 1.98 ppm, and the CH2 comes at 3.40. You can very easily calculate the chemical shift of these protons. Okay, and see, these are the coupling constant. JB is 6.7 hertz, JBC is 6.6 hertz, and JCD is 5 hertz. And say they are all these coupling constants are within 1 hertz range. Okay, so that's why you don't get these finer couplings. Okay, so almost they are being considered as equal. So that's why if you see, now these two methyls are equivalent because of you have a sigma V plane in this molecule, so they will come in the same place and they will have only one proton to couple, so you are getting a doublet here. with 1:1. Okay, your next proton is this CH. Now this CH is having 6 equivalent methyl hydrogen protons and 2 hydrogens whose chemical shifts are very close, 6.6. So you can consider they are almost equal. So if you consider 6 plus 2, there will be 8. So you should get a 9-line spectrum. And you can see there are 9 lines, 3, 4, 5, 6, 7, 8, and 9. Okay, clearly, and the spacing between them will be more or less average of these lines. Okay, one can find out from the here the chemical shift values are being given. Okay, and now the OH, this OH is coupled to only the CH2, so it is coming triplet, and this CH2 is now coupled to this hydrogen and this hydrogen whose coupling constants are very close. So that's why again here you are getting N+1 a triplet. Clear? So if the coupling constants are very close, then you can apply the N plus rule. But if it is more than the difference, if the coupling constant value difference are more than 1 Hertz, you have to consider the couplings separate. Now we'll see some heteronuclear spin-spin coupling. Heteronuclear means you will see in molecules there are fluorine, carbon 13, phosphorus, 15 nitrogen, whose I value is half. For example, I have shown for, let us say you consider this molecule, the CH2F2, okay, 13C, where carbon is also 13C. Okay, so you will see here 2 fluorines are equivalent and 2 hydrogens are also equivalent due to C2 and sigma p. Okay, so what you will see in 1H spectrum of in 1H spectrum, you will not see that fluorine and carbon peaks are coming. So you will see in proton spectrum only proton, no fluorine, because fluorine and carbon have totally very different resonance frequency in the proton because they have different gyromagnetic ratio. Similarly, in case of fluorine NMR, you will not see proton and carbon, and similarly for carbon also you will not see hydrogen and fluorine. So that means you detect one isotope at a time. So what you will see in, if you record a proton NMR spectrum, okay, so as the 2 hydrogens are chemically equivalent, so they have the same delta value, but now it will be first split by carbon 13, a 1:1 doublet, and then each line will be split by 2 equivalent fluorine to 1:2:1 triplet. So what you will see that you will have a pattern like this. Okay, so this is coming due to the fluorine JHF, and this is due to JCH. Okay, I have already mentioned that 1 JCH is much larger than the 2 JFH. Okay, so this is the this intensity will be same. So this is your the appearance of your proton spectrum. Now so the separate this will give you the JFH, sorry, not this, these 2 line separation of these 2 lines will give you the JFH. This is your JFH and this is your JCH. Okay, now what you will see in fluorine spectrum, also you will see very similar. Okay, very similar, like proton only. But if you go to the carbon 13 also, so in carbon 13, how we'll see? So carbon 13 will be first split by 2 protons. So this will be okay. So yes, 13 C spectrum. You see that. No, so fluorine spectrum, what you will see, so this is your 13C spectrum. Okay, so your chemical shift value is this. So these 2 are due to JCH, and sorry, this is so let us do the proton. Okay, I think I'm doing something wrong. So let us see, you have a proton, okay, when there is no coupling. Now you are coupling to a carbon, so you will get a doublet. Now each doublet will be split into a triplet due to coupling. So this will be your JHF, This is your JCH. So actual final spectra is like this, and this will be your chemical shift. Okay, so that is your hydrogen. Now let us come to fluorine. So fluorine case also you will get the same thing. Now let us see for carbon. So carbon, what you will see, carbon, if there is no coupling, you get a one line. Now it is coupled to two. Fluorine, the coupling is larger. I have mentioned that. So you will have a triplet. You will have so make it a little bigger triplet. So I'll make a triplet. This is nothing but JFC. Okay. Now you see I am bringing now hydrogen coupling. There are two equivalent hydrogen. So each line will be similarly. This line also similarly. So this will be a triplet of triplet spectrum. This will be a doublet of triplet, and this will also be a doublet of triplet. Okay, so it will be a doublet of triplet, and you see fluorine spectrum will also be a doublet of triplet, but in case of carbon 13 you will have a triplet of triplet. Okay, so you can first draw the one nuclei, and then you saw the first draw the larger coupling, and then each line again use, because you have to now use the to multiply the various okay. Now the question comes, why don't we see proton 13 in proton NMR spectrum, the 13 coupling in 13C coupling? Why you do? The reason is that because the 13C abundance is 1.1%. So you will see that about 1%, 1.1% protons only will have carbon 13 coupling. Okay, so that's why the peaks are very small and we neglect it. But you can see if you blow it up, this is the J13CH. You can see this is the TMS peak, and you can see the fraction of that molecule which are having carbon 13 is now can be seen here. Okay, so if the natural abundance of a NMR active nuclei is low, the peaks due to coupling of that nuclei appears as satellite peak in proton NMR spectra. Okay, and if it is falls below 1, you may not be able to see it. So you can see this is a very interesting molecule, the bis-trimethylsilyl mercury, where several almost all nuclei are having NMR active. So you see the first thing is that the proton abundance, proton, we are recording the proton NMR. So this is coming from your these protons are not coupled to any of these other nuclei. Okay, and then you see the 29 silicon. 29 silicon is about 4.7%. You see that a small satellite here and a small satellite here. So that doublet is coming due to proton silicon coupling. And then this is your 16.9% mercury. Mercury 199, which is NMR active, that is also spin is equal to half. You see, because the percentage is quite large, you can see a coupling. And there is distant one, this and this, they are coming from the 13C, because 13C about 1.1%. So this is the way, if you really blow up the spectra, you can see coupling due to almost all possible nuclei. But normally we don't see. When you bring everything into scale, you will see they will be probably merging in the noise or in the baseline. Now this is the carbon 13 NMR spectra of 2-chlorobutane, and if you see in this, so in carbon 13 spectrum, if you remember, I told you that when there is a very or rare chance that two adjacent carbon will be carbon 13. So you never see a carbon 13 coupling in carbon 13 NMR spectrum except you make the label compound. Okay, if you specifically make it, you will see it. Okay, now you see here that already I have told that maximum we see the coupling the up to 3 bond. So you can see that up to 3 bond, but if you see the JCH, the 1 JCH is very large. Okay, and 2 and 3 are very small. That's why if you see that your this carbon, the carbon D that comes where around 10 ppm is coming as a triplet and quartet. The quartet is coming due to the 3 equivalent hydrogen and these two. So these two hydrogen and these hydrogens are coupled. So similarly, this one is also a doublet of quartet because there is only one proton, okay, which is at 3. So you are getting a doublet of quartet that is around 25. And then this CH2 is coming as a, now this CH2 will be triplet due to these two hydrogens, then a quartet due to this methyl and doublet. So that's why it will be a DTQ or TDQ depending on what is the chemical the coupling constant value. You can write any TDQ or DTQ, does not matter. And then you have this CH that comes as a DTQ because it is coupled to this CH3 as well as this CH2. Okay, but only you can see the larger coupling constants. Others here you can see small values can be seen here. Okay, now same thing you so this is the same spectra I am showing here. Now if you do a proton decoupling, that means you are removing the couplings of proton, okay, from the carbon spectra, and you will see all the carbons will now come as a signal. So now see, this carbon has become singlet, this carbon has also become singlet, this also become a single line, this also become a single line. Okay, so this is the way normally carbon 13 spectra is recorded after decoupling. Okay, and that's why you see now all carbons they have different intensity, and I have already mentioned you that why the carbon 13 spectra are not integrated because of the nuclear Oberhauser effect and the relaxation time. I will discuss those things later on. Okay, see, most important thing here is you see the CDCl3 peak. Okay, it gives you a 1:1:1 triplet. Okay, so let us now see that heteronuclear coupling. Heteronuclear means we will say that when the I value is greater than half. Okay, so if you see, notice the CDCl3 there you are getting a 3 equally intense line. So where from it is coming? Okay, and if you see the coupling constant between them is JCD is 31.8 Hertz, that you can find out. Okay, so let us see where from that scheme is coming. Okay, so we know the spin value of I is spin value of deuterium is 1. So in CDCl3 1D, and it can have 3 spin combinations. If you use the same formula, I is equal to 1 for deuterium. So and there are 3 possible spin states. Okay, that also I have shown here. Here M it's because only there are only one deuterium. So all 3 possible things Mi values are actually the capital M value, and so automatically you see that now you will see that the deuterium the carbon nucleus is experiencing 3 different fields, one due to this, another due to this, another due to this, and this is nothing but your the chemical shift value. Okay, and this is your 1JCD value. Okay, so now you know the reason, because they have all 3 have the equal probability and you are getting the same intensity. Unlike your proton NMR triplet, which is 1:2:1. So we can tell these also triplet. So you must now remember that the triplet from proton NMR is different from triplet in when you consider the CDCl3. Okay, now let us see the NMR of CH2D2. How it will look like when there are 2 deuteriums. So now when you have 2 deuteriums, there are 9 possible combinations, spin combination, and you will have now 5 possible spin state, which I have shown here. There are 5 possible. This is one, this is another one, this is. So you will see that they have a relative this thing. This is 1, this is 2, this is 3, this is 2, this is 1, and that is the way the relative intensities have been described. So these two are the you can say the plus 1 state. This is 0, mi is equal to 0, and here both the mi is equal to. So this is your m is equal to 2, m is equal to 1, m is equal to 0. This can happen from this combination, and this combination, and this is m is equal to -1, m is equal to -2, and you get now when you have 2 deuteriums, now you see there are 5 lines, and then the relative ratio will be 1:2:3:2:1. So you can find out this type of things for any combination of nuclei. Okay. So if a nuclei couple simultaneously, you see, if a nuclei couple simultaneously to any number of A nuclei with spin value IA, NB number of B nuclei with spin value of IB, NC number of C nuclei with spin value of IC, and then total number of lines or multiplicity is given by. So this is the 2 times of number of A-type nuclei, the spin value of the A nuclei in plus 1 into 2 times of, you can see the B nuclei, IB, and similarly the other nuclei. So that gives you the total multiplicity, whether you get 5 lines, 10 lines, 15 lines. Okay, that will be decided by this. And here I see this is self-explanatory. You read it. Even if you do not understand, I have clearly written here. Suppose you take a acetone D6, okay, and let us say that is small amount of 1 hydrogen is there. This is acetone. 1 methyl is CD3. Another, there are 2 deuteriums. You have to tell about how the proton NMR look like, how the carbon 13 will look like, okay, how the deuterium NMR will look like. That I have already clearly written, and why it is happening, everything is there. Okay, so it is self-explanatory. If you do not understand, you can ask me. Same thing, I have given another molecule CH2DF2. Okay, here deuterium is also there, fluorine is also there, and you can find out how the proton will look like, how the 2D deuterium NMR will look like, how the fluorine NMR will look like. So they are clearly written here. Okay, so if you have any doubt, you can ask me. These two you must try to understand yourself. If you have any difficulty, I have explained you how we are doing, and also here clearly written how I have done. Okay, थोड़ा ये करो, connect करो, unmute कर दो इसको, बोल दो, they can ask. ঠিক আছে পাল্লা, ভালো আছে। সময় নেই এগুলো দেখা, না এগুলো লেখা আছে ক্লিয়ারলি। হ্যাঁ বুঝ from anybody? All are unmuted, so you can ask. All are unmuted. Okay, if you feel that you what you have to do, you have to go through the lecture and last 2 problems, which I have just written, but I have not drawn the scheme. Okay, you try to draw the scheme and see. Okay. So your next class is tomorrow at 4 o'clock, 4 p.m. Okay. Okay, so if there is no doubt or question, then I'll close it here. Okay, and then see you tomorrow, all of you. Thank you.